So this will be a short video about implicit differentiation. So thinking back to the different rules of differentiation that you guys know up to implicit differentiation. Like if you wanted to differentiate y equals to x cubed, you could just think about using power rule. You could say that's y prime equals to 3x squared. You could say that's dy over dx equals to 3x squared. If function notation were being used, like that was f of x equals x cubed, you could say the derivative is f prime of x is equal to 3x squared. But you can also differentiate y equals to x cubed or any of the functions you've been studying from an implicit differentiation perspective. And when we're using implicit differentiation to differentiate or find the derivative of a function, we're thinking chain rule, chain rule, chain rule. Just a reminder, chain rule is if you have a composite function where you think of having a function on the outside and then a function on the inside. I always think of the Russian nesting dolls whenever I think of composite functions. So to differentiate a composite function, you need to use chain rule, where the derivative y prime would be the derivative of the outside function. You leave the inside function alone, and then you multiply by the derivative of the inside function. So to differentiate y equals to x cubed from an implicit differentiation perspective, and we're thinking of differentiating with respect to x, we first need to show that we're differentiating with respect to x. On the left-hand side, differentiating y with respect to x, that can just be written as dy over dx. That's another way to read dy over dx is the derivative of y with respect to x. But then on the right-hand side, we can think of x cubed as a function in a function, where the cube, the exponent of 3, is the outside function, and the x, here, outside function, the x is the inside function. So thinking chain rule, derivative of the outside would be bring the 3 down, subtract 1 from the exponent. Then we leave the inside alone and multiply by the derivative of the inside with respect to x, which would be the derivative of x with respect to x. That can be written as dx over dx. Well, dx over dx is just 1, so we can see that dy over dx is 3x squared. It's obviously a lot easier to just think power rule for finding the derivative of a function like y equals to x cubed, or any equation where you're differentiating with respect to the given independent variable. Or usually in our case with respect to x, it's easier to just apply where you have y equals to the rule of the function. It makes sense to just use our regular rules of differentiation. So power rule, product rule, quotient rule, chain rule. But you can also think of from an implicit differentiation perspective, which might be helpful then. Like if we took that same equation and thought about differentiating with respect to t, we would have to use implicit differentiation. On the left-hand side, the derivative of y with respect to t would be dy over dt. And then on the right-hand side, again, thinking of the exponent of 3 as the outside function, the x as the inside, we bring the 3 down, and subtract 1 from the exponent to differentiate the outside. We leave the inside alone, and then the derivative of the inside x with respect to t is dx over dt. So dy over dt equals 3x squared times dx over dt. Just one more quick example here. How about a Pythagorean theorem? So differentiating with respect to t each term. So for each term, we're thinking of the exponent of 2 as being the outside function, and then the x or the y or the z as being the inside. So when we differentiate x squared with respect to t, we bring the 2 down. If you think about subtracting 1 from the exponent, leave the inside alone, and then times the derivative of x with respect to t. Okay, then same thing for the y squared term. So bring the 2 down, subtract 1 from the exponent, leave the inside alone, multiply by the derivative of the inside with respect to t is dy over dt. And then same with the z term, or the z squared. Oops. Times dz over dt. Derivative of z with respect to t. Okay, and that could just be simplified to be 2x times dx over dt plus 2y times dy over dt times 2z, or equals to 2z times dz over dt. And then we can apply additional rules while we're using implicit differentiation. So if we had something like x times y equals, I don't know, 2. Or how about x squared? X, how about 2x to the 4th? Okay, so if we want to differentiate with respect to t, we show that we're differentiating with respect to t. We could pull the 2 out. You could leave it inside the parentheses or pull it out. It's your preference. On the left-hand side, we have a product. So we need to think product rule. So first factor times the derivative of the second factor. Well, the derivative of y with respect to t is dy over dt. Plus the second factor times the derivative of the first factor, which would be dx over dt. And then on the right-hand side, differentiating that x to the 4th term, we bring the 4 down and multiply by the 2. Subtract 1 from the exponent. Leave the inside alone, and then multiply by the derivative of the inside with respect to t. So it depends what you want to do with this equation. Like if you wanted to solve for dx over dt, you could by getting all the dx over dt's on one side of the equation and isolating. But for related rates problems, we're really just having to differentiate with respect to t, and then we're plugging values in. Hope this helps.